So, you're taking a thermodynamics class, or talking about thermodynamics in a chemistry class, and standard latent heat has been brought up by your instructor. You may be unsure as to what they were talking about, and all of a sudden, you find yourself here. Well, let's discuss standard latent heat. If you've ever put an ice cube in a glass of water or a soda, you've probably realized that it did not melt instantly. That's because there is a certain amount of heat required to melt the solid ice to liquid water. This is considered to be standard latent heat of fusion. It's the amount of heat in kilojoules per kilogram that's needed to melt a substance. There's also something called the standard latent heat of vaporization. This is the amount of heat required to change a substance from a liquid to a gas. If you're boiling some water to cook up some Kraft dinner on the stove, you again notice that once the water begins to boil, it doesn't all boil off at once. There's a certain amount of heat needed to change all of the liquid water to gaseous water. Because this is important information, of course there's a formula that can help us figure out how much heat is needed to change the state of a substance. First, it depends on the substance itself, as different substances will have different standard latent heat values. Secondly, it depends on the mass of the substance. In other words, how much of the substance is changing states. Let's go ahead and take a look. So in this example, it asks how much heat is required to melt 205 grams of solid water at 0 degrees Celsius to liquid water at 0 degrees Celsius. And we have the standard latent heat of fusion for H2O right there. But before we begin taking a look at this, we should look at a heat curve for water. So let's go ahead and do that. So here we have a general heat curve, and it's worth it to notice we have our temperature on our y-axis, and we have quantity of heat on our x. So here, substances are going to be in their solid state when the temperature is the lowest and the least amount of heat has been applied to it. And from there, they can melt into a liquid as heat is added, and from liquid they will boil into a gas as more heat is added. Okay, so in our question, we are going to be calculating how much heat it takes 205 grams of water to go from 0 degrees as a solid to 0 degrees as a liquid. So if we take a look at the melting stage on this heat curve, we notice that there's no temperature change, but only an amount of heat added. So when creating the formula, all we need to take into consideration is, first, the quantity of heat, then we need to take into consideration the mass, and finally, we need the standard latent heat of fusion for that substance. We do not need to bring temperature change into this formula because there's no temperature change while there's a change of state. So back to our question, we know we have the formula Q is equal to mass multiplied by the latent heat of fusion, and we have some values as well. We know our mass is 205 grams, but let's convert that to kilograms because that's what our latent heat of fusion value is in. So 205 grams is equal to 0.205 kilograms, and we know our latent heat of fusion value for water is going to be 334 kilojoules per kilogram, and we can go ahead and plug these into our new formula. So we have Q is equal to the mass, which is 0.205 kilograms, multiplied by 334 kilojoules per kilogram. Just quick talk about our units. Kilograms is going to be gone, and we can go ahead and calculate our answer. Once you throw that into your calculator, folks, you should get 68.47 kilojoules of heat is required to melt this 205 grams of water. And you know what? Why don't we round this to 68.5 kilojoules? Let's move on. Our next example reads, how much heat needs to be lost in order to turn 155 grams of liquid water at 48 degrees Celsius to solid ice at negative 19 degrees Celsius? And we are given a little bit of information here. First off, we have the specific heat capacity of water as a liquid as 4.184 kilojoules per kilogram degrees Celsius. So all that means is that it takes 4.184 kilojoules of heat to heat 1 kilogram of liquid water by 1 degree Celsius. And we also have the specific heat capacity of water as a solid, and it's going to be 2.10 kilojoules per kilogram degrees Celsius. But before we start going over this, let's head back to our general heat curve. Okay, we are back at our heat curve, but we are dealing with a little bit of a different scenario. Last time, all we had to figure out was how much heat it took water at 0 degrees Celsius as a solid to melt to 0 degrees Celsius as a liquid. So we were really only doing this part of our heat curve, and we could use Q equals the mass multiplied by the latent heat of fusion. But this time, we are going to switch it up a little bit. We're going to add a few steps here, all right? So we are starting at 48 degrees Celsius, and we are going all the way down to negative 19 degrees Celsius. And there's going to be 3 different steps here. The first step is we are going from 48 degrees Celsius to 0 degrees Celsius, and that is in liquid state. So we have 48 degrees Celsius as a liquid to 0 degrees Celsius as a liquid, but there's no change in state, so we can use Q equals mc delta T. So we have the mass, the specific heat capacity of water as a liquid, and the temperature change it experiences. That's going to be step 1. Step 2 is similar to our first example, where we are calculating how much heat needs to be lost in order for the water at 0 degrees Celsius to freeze into water as a solid. So step 2 is 0 degrees Celsius as a liquid to 0 degrees Celsius as a solid. And because of that state change, we need to use our Q equals the mass multiplied by the latent heat of fusion, but just as a negative value because it's losing that heat. And finally, step 3, we are going from water as a solid, so at 0 degrees Celsius, all the way down to water as a solid at negative 19 degrees Celsius. So we have 0 degrees Celsius as a solid. I'll write that a little bit neater. Whoops, there we go. To water at 19 degrees Celsius, and it'll still be a solid then. And we can be using our Q equals mc delta T formula once again because of that temperature change. And we're also going to talk about our C value changing because water is no longer a liquid, it's a solid. All right, let's get into it. So like we were saying in our general heat curve conversation, step 1 is going to be with Q equals mc delta T to calculate the amount of heat lost as the water in liquid form goes from 48 degrees Celsius down to 0 degrees Celsius. So Q is equal to our mass, which is going to be 155 grams, but again, I am going to convert to kilograms because that is what is found in our C value of water as a liquid. So 155 grams is equal to 0.155 kilograms multiplied by our C, which is 4.184 kilojoules per kilogram degrees Celsius. And that's multiplied by the temperature change, which is going to be from 48 degrees Celsius down to 0 degrees Celsius. So it's going to be negative 48 degrees Celsius. Okay, and again, quick talk about our units. Kilograms is canceled out. Degrees Celsius is also canceled out. So what we're left with as our Q value for step 1 is going to be kilojoules. So let's go ahead and calculate that. We have 0.155 multiplied by 4.184, and that is multiplied by negative 48. and you should get a Q value of negative 31.13 kilojoules, and that makes sense because if our water decreases in temperature, that means it loses heat. So our Q value should be negative. All right, let's keep going. So step 2 has us taking into account the state change of water. So we are back to using Q is equal to the mass multiplied by the latent heat of fusion. Okay, so we have Q equals the mass, which is 0.155 kilograms, and that is multiplied by negative 334 kilojoules per kilogram. So remember, because we are freezing, we are going from a liquid to a solid. This water needs to lose heat. So in order for 1 kilogram to freeze, it needs to lose 334 kilojoules of heat. So that's why we have a negative value for our latent heat of fusion. So we can go ahead and plug that in. So we have 0.155 multiplied by negative 334, and we get a Q of negative 51.77 kilojoules. Again, because our kilograms are canceled out, we end up with kilojoules as our unit. And let's move on. And finally, step number 3, we are going from 0 degrees as a solid down to negative 19 degrees as a solid. So therefore, we are going to be back to using Q equals mc delta T. So our mass hasn't changed. It's still going to be 0.155 kilograms. Our C value has changed because we are no longer H2O as a liquid. We are H2O as a solid. So we have our new value up here. It is going to be 2.10 kilojoules per kilogram degrees Celsius. And finally, our delta T is going to be negative 19 degrees Celsius. So we can go ahead and plug those in. We have 0.155 multiplied by 2.10 multiplied by negative 19. And we get a Q of negative 6.18 kilojoules. And once again, folks, our Q is negative, so that means heat has been lost from the system, and that makes sense since our temperature is decreasing. Let's move on to our final step. All our last step has us doing is adding up all of our different Q values to have one total Q. So I'll call this Q total is equal to step 1. So we have negative 31.13 kilojoules plus from step 2, negative 51.77 kilojoules plus from step 3, negative 6.18 kilojoules. And when we add all of those up, folks, let's go ahead and do that. So we have negative 31.13 plus negative 51.77 plus negative 6.18 kilojoules. We get a total of negative 89.08 kilojoules of heat. So that means 89.08 kilojoules of heat had to be lost in order for the water to go from 48 degrees Celsius all the way down to negative 19 degrees Celsius as ice. One last tidbit of information to leave you with. Anytime you are calculating a temperature change, you are going to be using Q equals mc delta T because that takes into consideration the temperature change of the substance as well as the specific heat capacity, and you need both of those to determine this Q. And anytime you are calculating the Q of a state change, you will be using Q is equal to mL, and it just depends on whether it's going from a liquid to a gas, you would be using the mLV for vaporization, or if it's going from a solid to a liquid, you would be using the latent heat of fusion like we did in this video. All right. If this video did help you though, please like and subscribe. Thank you very much.